Alright, so I think we're back. Okay, so, like I said, I didn't hit the shift. Alright, so we derived our critical buckling load and our critical buckling stress, but the thing that we didn't take into account are boundary conditions. Now, this is what I was saying earlier. For those of you who decide to take steel design for you civil engineers, this is a little bit of a spoiler alert, but when we look at columns in buildings, we take Euler buckling and we really break it down, because there's a lot of issues with Euler buckling that make it not so directly applicable to structural design. Mainly the idea that members aren't perfectly straight, members have internal residual stresses. For common scenarios, you can find formulas that are derived and set up and ready to go for you. The good thing is that pretty much all of those formulas and models use elastic buckling, so it's still a very useful concept. But one thing that we can handle very easily is what happens if our boundary conditions change. If I go back a few slides, see, here's our column. And when we assumed that it buckled, we assumed a pin-pin boundary condition. This is pinned and this is pinned. So what happens if those boundary conditions change? What if it's fixed on both ends? What if it's fixed and free and what have you? So let me go forward a little bit. So what happens if the boundary conditions are changed? So let's say I have a column that looks like this. Okay, and I picked this column for a very specific reason. Okay, I have here a column that's fixed free, so it's fixed on the bottom and it's free on the top. Now, if it's free or if it's fixed on the bottom, it's not going to translate or rotate. So, imagine you have like a light pole sticking out of the ground, and we apply a compressive load on the top. It's probably going to buckle or bow out something about like this. Okay? Well, if I use the formula that I previously derived by itself, it's not going to work because the boundary conditions aren't the same. Remember when we derived that formula, remember we had arbitrary constants, we had C1 and C2, and we solved for those constants using our boundary conditions. Well, our boundary conditions have changed. It's not the same column. So that formula isn't going to work. But maybe there's a way I can tweak that formula. Maybe there's a way I can adjust some of the parameters in that formula to make it work, to force it to work. The answer, can I do that? The answer is yes, you can. And you do that through the use of an effective length factor. We call that effective length factor K for columns. So let me explain how K works. Okay, everybody agrees that this is what the buckled shape of this column looks like, right? Okay, now what I'm going to do is imagine that this buckled shape sort of continues. Okay, so what do I mean? Here I have a pin-pin column. Okay, our effective length factor, essentially what it does is it modifies the length of a column so that it looks like this. Okay, so for the pin-pin column, K is 1. Okay, because if I have 1 times the length, I have the original length, and the formula doesn't change. But what I want to do is, can I determine different K values for different columns to relate it to this? Here's that fixed free column. If I continued that deflected shape, if I said, well, let's draw that deflected shape out, and let's see, that looks a whole lot like how the pin-pin column buckles, doesn't it? Right? Now, how long is that column? How long is that deflected shape? Well, it's not the length, it's 2 times the length, right? So what I propose is that any time that you have a column that's, let's say, fixed on the bottom and free on the top, I propose that its effective length factor is 2, okay? Because that's how long, that's the length that compares the difference between this fixed free column and our pin-pin column that we were trying to relate to earlier. Does that make sense? All right, everybody okay with this? So, first off, there are different K values for different scenarios. For instance, if our column is fixed free, the K value is 2. If it's pin-pin, that's our original scenario, and K is 1. If you have a column that's fixed on the top and fixed on the bottom, like it's clamped on both ends and you're applying a compressive value, your K value is 0.5. If it's fixed on one end and pinned on the other, we take the K value to be 0.7. Okay? And that's just drawing those out. So for instance, the fixed. Okay? if you look at, sorry, I did that backwards. If you look at a fixed column that's buckled, it kind of looks something like that. That's a horrible artistic rendering by me. But really, that's the shape that we're after, because that's representative of the fixed free column. And I propose that if this dimension is L, that this dimension here is basically about 0.5 L. So that's why this value is 0.5. Does that make sense? For the, and this is where my artistic ability lacks a little bit. If you have a column that's fixed on the bottom but pinned on the top, it sort of buckles like that. That's kind of how it buckles, because the bottom can't rotate. And that deflected shape, we're kind of after that. And we're saying that dimension is about 0.7 L. Does that make sense? Are we okay with that? So really, everything that's on this slide is pretty much everything that you need in order to determine buckling loads. Okay, so we have all of our K values, we have our critical buckling load and our critical buckling stress, and then the only term that's probably a little new is the, is the radius of gyration. And the radius of gyration is just the square root of I over A. Okay? Sound good? That sounds good. Let's do some problems. Okay. So I got a 2x4 wooden element, okay, and for this problem we're actually going to use the 2 inches and the 4 inches. For you civil engineers, I know you know that if you actually have a 2x4, it is not 2 inches by 4 inches, it's planed down a bit. But for the sake of this problem, just to keep everything simple, we'll use 2 inches and 4 inches. So I have a 2x4 wooden element that's used as a column with fixed ends. So I got a 2x4, I'm clamping each end and I'm pressing on it. Now this is wood, so I'm taking its E value to be 1600 KSI. And I want to determine the following. What is the column's maximum permissible length if the allowable stress is 5 KSI? And what's the central load that can be carried if the column is 8 feet long? So this is actually, I'd say, somewhat of a little bit more of a challenging buckling problem, but if you can handle this, you can probably handle just about anything. So let's do a couple things. So first off, let's compute some section properties. Okay, so this section is 2 inches by 4 inches. So just so we're aware, what's the area? It's 8 square inches. That's easy. Okay, now, this is where I want you to put your thinking cap on, okay? This is a rectangle, right? So what's the moment of inertia? Okay, BH cubed over 12. Now, that would seem to be the right answer, but it's wrong. Okay, and I'm going to explain why. All right, let's draw out our cross section. So here's the cross section, and this is 2 inches, and this is 4 inches. So let's say, for the sake of discussion, that this is B and this is H, right? The big thing to keep in mind is, let's keep the behavior in the back of our head. What are we talking about here? We're talking about buckling. Remember the example that I used last time of the yardstick? The yardstick, if I take a yardstick and I press on it, it's going to buckle whichever way it's going to buckle. It's going to buckle the easy way, not the hard way, right? It's going to buckle about the weak axis, not about the strong axis. So I propose that instead of using BH cubed over 12, we're going to use B cubed H over 12. We're going to use the width as the, the 4 inches and the height as the 2 inches. Okay? And you'll see we can follow this mathematically and see why this works, but just bear with me for a second. So what does this come out to be? First off, it's a moment of inertia, so it's going to be in inches to the fourth.
8/3.
8/3 or 2.67?
Yep.
All right, so 2.67. And then we'll go ahead and compute a radius of gyration. This is a new one. And so what does that come out to be? Square root of I over A. First off, what are the units? It's a radius of gyration.
Inches.
Inches.
.58.
0.58. I'm gonna carry it out one more. 577.
All right.
Is that about right?
Yeah.
I'm just gonna carry it out one more. I just want to make the value a little more defined, and I don't know why I'm just being particular, but I am. Now, this column, what are the boundary conditions for this column? Is it pen? What's the deal?
Fixed.
It's fixed. So if I have a column that's fixed, so let's look over here, fixed. What is K going to be? 0.5. Okay. So, if that's the case, now we can start doing some counts. Okay. So, part A. Okay, so what is the column's maximum permissible length if the allowable stress is 5 KSI? Let's see what happens. All right. Okay. Allowable stress is 5 KSI. Okay. We're going to do some figuring because I just want to see what happens. Okay. Let's just see what happens. First off, let's just ignore buckling. Let's say buckling doesn't exist. Buckling's a made-up phenomenon. Okay. It doesn't exist. Ignore buckling. It's not made up. Let's ignore it. Okay. If I have an allowable axial stress of 5 KSI, if we're not considering buckling at all, what is the allowable load? The allowable force.
5 times the area.
5 times the area, right? Sigma equals P over A, right? So let's compute a P allowable, which is sigma allowable times the area. So 5 KSI times 8, which is 40 kips. I just want to keep that in the back of our head. Now, let's consider the effects of buckling. Okay? So how do we compute a critical buckling stress? Here, let me put this in blue. So how do we compute a critical buckling stress? We take pi squared E divided by KL over R squared, right? Now, what the problem is saying this, it's asking what is the maximum length of the column so that its allowable stress doesn't exceed 5 KSI. So why don't I set its critical buckling stress to 5 KSI and let's solve. Well, what do we not know? We know E, right? That was given, it was 1600. We know R, we know K, we don't know L, right? So we can take this equation, rearrange it a bit, and solve for the length, okay? So how do we do that? Well, we have E divided by KL over R squared. Can I flip and multiply and say can I do that? Just flip around? Why don't I then take the square root? I can do that, right? And then I'm solving for the length, so what do? I flip the R and the K. So therefore, the length, and what this basically is a maximum length, and we'll explain why it's a maximum length here in a second, is R over K times the square root of pi squared E over sigma allowed. Right? So what do we have? We have 0.577 inches over 0.5, and then the square root of pi squared 1600 KSI over 5 KSI. Now, while some of you do the math, let me ask you a question. What are the units for the length going to come out to be? Inches, right? Because everything that happens inside the square root vanishes. So the only thing that's left is that. Say it again.
20.5.
20.5
Yeah.
for this.
Oh wait, never mind. I did 160. So 60. 64.85.
64.85. Do I have a second on that? And that's inches, right? Or how many feet is that?
5 foot 4 inches.
Well, 5 point however many feet. 0.4. I got like 4 of 1. Is that about right? Okay. So, first off, that's our answer. Now, let me ask you a couple questions. First off, why is that a maximum length? Like, let's think about buck length, all right? If a column gets longer, does it get weaker or stronger?
Weaker.
It gets weaker because, look at it mathematically, as the length goes up, the slenderness goes up, because that's L over R, or K over R. And if your slenderness goes up, your allowable stress and ultimately your load goes down, right? Okay? So that's why this is a maximum length, because any longer the column's going to get weaker. Sound good? All right. Now, this is not completely necessary. I'm just wanting to do this off to the side. This has absolutely nothing to do with this part. And I actually don't have this on my notes. I'm just curious to see what happens. I'll put this in a little bubble here on the bottom. Let's compute P critical for part A. So pi squared EI divided by KL squared.
Using this L.
Using this L. That's why I say, that's why I have, the way I labeled it, I put P critical for A. So, on the top we have pi squared, 1600 KSI. Our I value, what is that, 2.67? And then on the bottom, we got brackets here because we got 0.5. Now which value do I use, the 5.41 or the 64.85? There you go, exactly right, everything's in inches. 40.1. Kit, right? That's actually kind of an interesting result. That's an interesting result. Because what that's saying is that, hold on, let me close that door so I'm not wasting space. What that's saying is that this load and this load right here are right about at the same place. Okay, so it's actually kind of an interesting result. Our length of our column is 5.41 feet. Okay, this is what I propose. Okay, if this column gets longer, and I mean a lot longer, I propose it's going to buckle before it's going to crush. In other words, this column can only handle 5 KSI. Okay. So imagine, instead of this column being 5 feet, imagine if this column's like 5 inches tall. It's only about this tall. It's not going to buckle, right? I'm going to load it, load it, load it. It's just the wood is just going to crush, right? It's going to crush at a load of about 40 kips. But if the column gets longer and longer and longer, it's going to buckle before it crushes. Does that kind of make sense? We're probably going to have a different comparison here on part B. I just want you to keep that in the back of your head. Just keep that in the back of your head. Okay. Let's look at part B. So part B is asking, what is the All right, my phone went off. I can't really say anything. I could, but I won't. It would be rather hypocritical. What central load can be carried if the column is 8 foot long? So let's see what happens. What happens if the column is 8 foot long? Okay. So I propose that for part B, we have an L of 8 feet. So therefore, we can compute this pretty easily. So pretty straightforward. It's actually a very similar calculation. Now what do I put here? 8 feet?
96.
There we go. 96 inches. I put an inch sign there. That's not correct. So what does that come out to be?
18.3.
18.3. Do I have a second on that? Okay. All right. Here's the point I want to get across. Okay, on part B, the column is 8 feet long, right? Okay? On part B, the column's 8 foot long. It has a buckling capacity of 18.3 kips. Now, if you compare that to this value right here, I'm gonna box this in red because this is kind of important. Okay. So the column is 8 foot long. You tell me, is the column going to buckle or is it going to crush? If I start applying load for the column in part B, what's going to happen first? It's going to buckle, right? Because here's the load. I've got 1 kip, 2 kip, 3 kip, 4 kip, blah, blah, blah. And when I hit 18 kips, it's going to buckle before it hits that, right? Sound good? So I propose that if I have a column that's 8 foot long, that's its capacity. All right? Now, if you're paying attention, let me ask you this. What is the capacity of a column that's 1 foot long? Pop quiz. What's the capacity if it's 1 foot long? Like, go ahead and compute this if it's 1 foot, 12 inches. What's that?
0.2. Oh, wait, 912.
What?
And did 912, so 12.
I know I already drank some.
1170.
1,170 kips, right? So, you're telling me that a 1 foot long column is going to buckle at 1,170 kips.
It's gonna crush at 40 kips.
So how much can it hold up?
40.
40 kips. Did everybody see what I'm talking about? So we have the stability question, and that's answered by the buckling load, but then there's just its allowable stress before it crushes, okay? So if you sort of plot this out, what happens is if you look at the capacity gets lower and lower and lower the longer the column gets, but it gets cut off at a given point. So if you plot that out, what it looks like is this. Here, let me put this on the slide. So if you plot, let's say, like here's the length of the column, and here's the maximum load it can carry, what happens is this. The longer a column gets, the weaker it gets. Okay? And if you plot that out, it sort of looks like this, right? I mean, if the column was 8 foot long, you all got like what, 18.3 kips? And what'd you get if it was 1 foot long?
1,171.
This is 1 foot, and it was like 1,170 kips, something like that. But there is a point where you kind of have to say, you know what? All this doesn't matter because it needs to be cut off at 40 kips. That makes sense? So if you look at column curves, like a column curve, like a very, very common one or a very simple one, is that it looks like this. That this is P critical and this is P allowable. Does that make sense? So it's like, I don't care what the critical buckling was, it can't get over 40. That make sense? It's not too bad, right? It's just something I want you to be thinking about in the back of your head. Okay. Are there any questions? All right. Not only is this our last example, but watch this. Watch what happens when I hit next. That's the last slide. Holy crap, I know. Okay. I have this one. This one's a little bit of a design problem, but this one is where I'm sort of testing out your understanding of what we just talked about, how the capacities are cut off, and you'll see what I mean. Okay. A square steel bar has to support a load of 20,000 pounds on a length of 10 feet. Okay? For steel, we're going to take an E value of 30,000 KSI. And if the ends of the column are pinned, I want to design this cross-section, assuming that we either have 10 KSI steel or assuming we have 4 KSI steel. Okay. Sound good? All right, so let's see what we know about this column. Okay, so let's start off with the section properties. Same as we did before. Now, we do not know the size of this column. That's the whole point of the problem, is to determine how big this column needs to be. But we do know one thing about the column, and that's what? What's that? Well, we know the length. I'm talking about it in terms of its cross-section. What was the key word? It's square. Okay? So, if I have a column that's, let's say, b wide and b tall, what's the area? B squared. Okay? What about the moment of inertia? Well, because it's square, we don't have to worry about whether or not it's bending this way or bending that way. Because it's square, the moments of inertia are going to be the same thing. So if the moment of inertia is bh cubed over 12, but b and h are the same thing, I propose that that's b to the 4th over 12, right? So if you understand that, then you understand that I over a is b to the 4th over 12b squared, which is b squared over 12, and r is the square root of I over a, which is b over the square root of 12. I know some 8th grade math teachers like, you can't have a square root on the bottom. We're engineers.
It's there even if you reduce it. So.
Yeah, so you could do b
square
square root of 12 over 12 or something like that. I don't have time for that. Okay. Sound good? Now, let's talk about the length, because you mentioned the length. There's some interesting things to determine there. How long is the column? 10 feet, which is 120 inches, okay? What is K for this column? 1, and it's K, or it's 1 because it's pin. So, KL is 120 inches, right? It was 120 times 1. And KL squared is 14,400 inches squared. So far, so good? One other thing I'm going to go ahead and determine is what's KL over R. Well, KL over R is going to be what? 120 inches times square root of 12 over b. Did I do that right? Just flip and multiply. So if that's the case, what's KL over R squared? This is where I'm going to need your help with the calculator. What is 120 times the square root of 12, and then square that?
$172,800.
And that's inches squared over b squared. What do we think? So far, so good? Okay. Okay. Now, here's the thing. Let's start off by determining critical buckling load. Okay? Let's look at this for a second. Pi squared EI over KL squared. Let's take a look at that. So, we have pi squared. Do we know E? That was given. It's like 30,000 KSI. So we know E. What about I? What's I?
B squared over 12.
No, not B squared.
B to the 4th.
B to the 4th over 12. And do we know KL squared?
Yeah.
Yeah, that's 140 or 14,400 square inches. What don't we know in that expression? B. So let's solve that out. Would you agree that b to the fourth is, we take p critical, we need to multiply it by the denominator, so 12 and that, and then on the bottom, pi squared 8. I do that right? Okay, so what do we got? Let's see. Well, hold on. Let's go back to the problem. Do we know P critical? Well, let's see. We know E. We know 12, all this. Do we know P critical? What are we going to take to be P critical for this? The 20,000 pounds, right? Because what we're trying to do is figure out what is the required dimensions of the column such that it won't buckle. So we're going to take the 20,000 pounds to be the critical buckling load. But do I put 20,000 in that equation?
20 kips.
I put 20 kips. Why am I putting 20 kips? Because E is in KSI. Okay. This is, again, track your units. Incredibly important. Okay. So this is 20 kips. We have a 12 that has no units. Bless you. 14,400 square inches, pi squared, and then 30,000 KSI. So the kips cancel, and then you have inches squared on the top, and then you have 1 over inches squared on the bottom. So you flip and multiply that, and you get inches to the fourth. So.
11.67.
Say it again.
11.67.
11.67. That's inches to the fourth. So what's B?
$1.85.
1.85 inches. Do I have a second on that?
Yeah.
Okay. So, is this the answer? I'm going to say no. I'm going to say this is the minimum dimension to prevent. I need coffee as well. Buckling. Well, you stole my thunder because I was bringing that up. All right. So the problem gave us 2 allowable stresses. Okay. If the ends of the column are pinned, determine the required dimensions of the cross section, assuming sigma allowable is 10 KSI, assuming sigma allowable is 4 KSI. Okay. So let's sort of handle that. Okay? Here's how I want to handle that. Resulting axial stress. Okay? So let's say that we apply 20 kips to this section. And let's say we take B to equal 1.85 inches. We know that A is going to be B squared. So from these, what is sigma? P over A, right? So that's what is that?
5.84.
Say it again.
5.84.
5.84. First off, is everybody okay with the math? Okay. If you're okay with the math, then let's do some figuring here. If I can get untangled here. Part A. If sigma allowable is 10 KSI, if sigma allowable is 10 KSI, I want everybody to pay attention. I'm going to ask a question. If this is true, what is going to happen first? Are we going to buckle the column, or are we going to crush the column? Well, now hold on. Would you agree that this is the dimension required to prevent buckling? All right? Okay? So, let me sort of walk through this. That's the dimension to prevent buckling. Let's say that this is the dimension. Let's say this is the column size. Okay? You would agree this is the dimension to prevent buckling. If I use a column with this dimension, that's the stress. So let's say I got a column that's 1.85 square inches, or 1.85 by 1.85. I put load on it. Okay? All right. I put 20 kips on it. It won't buckle because that's the minimum size to prevent buckling, and that's its stress. Is that an acceptable solution? Let me ask it that way. Would you let me ask you because I think I'm sort of asking in a confusing fashion. If I put 20 kips on this column, would you agree that's the stress? Okay. Is that stress acceptable compared to this? Is it? So, okay. This is what I propose. If sigma allowable is 10 KSI, then B required is 1.85 inches. Okay? For part B says if sigma allowable is 4 KSI, then what? Let's look at this scenario. Okay? Would you agree if I use a column of this size that that's the stress? Now under part B, is this acceptable? No. So I propose that if sigma allowable is 4 KSI, then B required has to be greater than 1.85 inches. Does that make sense? Now why am I hammering the 1.85 inches? Consider the problem. We know the load, we know the boundary conditions, we know the length of the column, okay? That is the dimension required to prevent buckling. What I'm asking is this enough? Well, if sigma allowable is 10 KSI, then yes, it is enough. But if sigma allowable is 4 KSI, then it's not. The column's got to be bigger. Because, yeah, it'll prevent buckling, but I propose that if sigma allowable is 4 KSI, you will crush that column before you buckle it. Does that make sense? I know that's a little bit of a tricky...
Can we be more specific?
What do you mean?
Like B should
what is it?
within the square root of P over A? Yeah, right.
I'm getting, yeah, you're exactly right. I'm getting to that.
I thought that was the...
No. If this is the case, how do you design this column? Very simply. Sigma allowable is P over A, which is P over B squared. So therefore, B is the square root of P over sigma allowable, which is 20 kips over 4 KSI. And what is that? What's the square root of 5?
2.2?
2.23 is it something? 2.24. All right. I know that's a little bit of a weird calculation, so let's sort of take a second and digest that. Make sure that we're clear on that. So the approach that we took on that problem is we said, let's ignore the part A and part B, and let's just figure out how much column is required to prevent buckling. Okay? So we determined that that's 1.85 inches. Then we asked the question, well, is that enough? Well, if sigma allowable is 10 KSI, then that's fine, because we don't get that much stress. Okay? But if sigma allowable is 4 KSI, then that's not enough column, and we just have to resort to regular old sigma equals P over A. And what do we get? Does the answer make sense? Well, yeah, it makes sense, because that answer is bigger than that. That's what we expected. Okay? What do we think? Any questions?
Is that only for square columns?
Well, the pattern that we're talking about, no. The only thing that is only true for square columns is that the area equals B squared. So like, for instance, if we had a circular column, I might say sigma equals P over A, which equals P over pi over 4D squared. And then I'd be solving for the diameter. Does that make sense? So the pattern could be the same for any column of any shape. The only difference is the actual formulas that you use might be a little different, because the area of a circle is not B squared. Right. Everybody else okay with that? So if you want a final answer, here's what I propose. I propose that for this scenario, B is 1.85 inches. For this scenario, 2.24 inches. And ignore all the buckling and all the math. I think the answer should make sense just looking at the allowable stresses. If your material can only handle so much stress, you have to use more of it, right? Now, one interesting thing about buckling, what if instead of assuming sigma allowable is 10 KSI, what if sigma allowable was 100 KSI? Would this value change any?
You could make it smaller.
No, because it's going to buckle elastically, right? Remember, this 1.85 had absolutely nothing to do with allowable stresses, all right? Does that make sense?
Yep.
I know this is where you're going to hike up your pants a little bit. What do you think?
So why can't you make your B dimension smaller if your allowable stress goes up? It'll buckle.
Because it'll buckle. Tell you what. Let's just make up a number. Okay? Let's say B equals 1.5 inches, right? Let's look at this right here. If B is 1.5 inches, what's P critical? Like, somebody tell me. Like, plug and chug and tell me what you get.
.67.
8.67, right? So I propose that if the column is 1.5 inches, it can only hold up 8.67 kips. What's the problem with that? This column has to hold up 20 kips, right? The column has to be at least this big to hold up 20 kips, okay? But remember, this check has absolutely nothing to do with allowable stresses. It has only something to do with elastic buckling, okay? What I'm getting at is this. We use this dimension to check the stress. We had a sigma, a critical buckling stress of 5.84 KSI. What I propose is this. As long as your allowable stress is over this, you're fine. So whether or not this was 10 KSI or whether or not it was 200 KSI, it doesn't matter. The column's capacity is still going to be 20 kips. So you're not, what I'm getting, you're not really getting much of an advantage in using a higher grade material because it's going to buckle whichever way it's going to buckle. Okay, so for instance, this is steel. Okay, so for steel, the E is what, 30,000 KSI? But different steel grades have different yield stresses. The more money you pay, the higher yield stress that you get. Okay, but for a situation like this, you're wasting your money because, yeah, you get a higher yield stress, a higher allowable stress, but it doesn't matter because it's going to buckle before it's going to yield or crush or what have you. That make sense? Out there stuff, right? Out there. Any questions? Well, seeing no questions, I don't have anything else to talk about. So, you know what we're not going to do? We're not going to meet on Tuesday. I'm giving you all the day off. But you still have a homework assignment to do. So, here's what we're going to do. I've given you a homework assignment today. It's due on Thursday. Okay? We do not have class on Tuesday, but obviously I'll be around, throughout this week and next week in case you all have any questions on the homework. Okay? You can also email me and whatnot. But this homework is really short, and I think it's fair to say, if I remember correctly, this homework is far easier than what we've done in class. Like, you can do what we did in class, you can definitely do the homework. We will meet on Thursday, next Thursday. You will turn in the homework. We will go through the homework solution and the exam review. You all ask whatever questions you want about the exam. We come in next Thursday, we take the exam. You all are done with Engineering 216. It should be Thursday at 8 o'clock, I think. Am I right? Yeah, it should be. Did I put the, I'm pretty sure I put it there. Now, hold on.
It's there, but there's not a time.
Oh, there's not? Yeah, I'm pretty sure it's 8 o'clock. Here, hold on. Let's just make sure I'm not completely wrong. I'm pretty sure it's at 8 o'clock.
Just whatever the university says to do. You don't have to yell at people.
Yeah, but look, the link was all caps. Okay, so fall 2018. Yeah, it's at 8 o'clock. So Thursday at 8 a.m. So. Any questions? You seem like in disbelief that it's over. We could meet Tuesday if you want. I'll come up with something to talk about. Talk about shear centers or beams on elastic foundations or plates. We're not talking about that. Oh, like plate analysis. You want to talk about some math. That is some math. That's some good stuff. Fourier series and partial differential equations. That's the good stuff. You're like, Dr. Mike, we're done. We're done. We don't care about anything you're saying right now. All right, guys, that's all I got. I will see you all next Thursday. So class is officially canceled on Tuesday.